So, welcome back to this week's last lecture of this course, Fundamentals of Attosecond Science and Technology, which we present from IIT Madras and IIT Tirupati. We are in the 7th lecture of this module. The module itself is on femtosecond laser pulses, and we have cleared quite some ground on this in this section. And just to remind ourselves, while thanking Professor Trebino for sharing his inputs and lecture materials, we will continue to refer to these key references, the books by Roulier and Chang, which are particular to femto and sub-femtosecond pulses in optics, and of course the book on the principles of optics itself. So, yes, I know we have this habit of recapping the essential elements from the previous lectures of this section. So, we will do that even faster or even quicker today, but we will continue our discussion on the phase terms. We elaborated quite a bit on on one of them in the previous lecture. We will take this forward and discuss including group delay dispersion, and then the concept of chirp and its characteristics. Okay, so light pulse, once again, we are getting very habituated to this time domain picture where the pulse has an envelope and instantaneous frequency in time. If we sketch the electric field amplitude, in this case time going in increasing direction of time going from left to right. So, the instantaneous frequency of this pulse is increasing with time. All of that is captured in this phase term of the electric field written in complex notation, where we identify a carrier frequency omega naught and all the other slower variations of the field described through phi of t, the phase function. Now, on similar scales as phi of t, which is time scales significantly slower than 1 over omega naught would designate, we also have the field envelope, which is the square root of I of t, related to the intensity envelope, which is I of t. And this motivates defining a complex amplitude, which is all this relatively slow variations in time sans the fast omega naught t carrier variation. That is the complex amplitude of the pulse, and the carrier, the definition of the carrier through omega naught completes the full description of the electric field when multiplied to this term, whereas the real amplitude itself could be defined as just the what we have written as the square root of I of t, or the term that is left after erasing e to the I phi of t. Okay, that is just the real part of this complex quantity, and we should not be tired of reminding ourselves that electric fields are real. So, you always have the real part of this of the full description of the field playing a role, and all these nuances arise out of a complex notation being employed by us. We have the field and amplitude envelopes, both of which could be Gaussian, and in the case of a Gaussian pulse, be related to each other through a square root of 2 factor. So, now we realized that, especially from the perspective of measurements, we will have to take recourse to the spectral domain, and that our ability to do things directly in the time domain are very limited, and it is indeed one of the hallmarks of attosecond science that for optical pulses this science and technology enables us to do things, play around directly in the time domain, but we will have to wait for that to happen a bit later in this course. Even so, the spectral domain or the frequency domain is very important, So, the description of the same electromagnetic phenomenon which we describe through the pulse electric field of the form E of t square root of I of t exponent I omega naught t minus phi of t, half of that plus complex conjugate, is the electromagnetic phenomenon of interest here. Equivalently, we can describe this in the frequency domain by Fourier transforming both pieces, the piece that is written here and its complex conjugate, and obtaining two terms on either side of the 0 of the frequency scale, where omega naught retains its important key position as the carrier frequency, and omega being the angular frequency variable. The arguments to these two pieces of functions on right hand side before and after the plus sign are one on the positive side of the frequency scale, other necessarily on the negative side with minus omega naught, where omega and omega naught are frequencies and hence positive numbers. So, we can analogously build a complex frequency domain pulse field of the following type: E tilde of omega, where we have square root of s of omega playing the role of the spectral real amplitude, or I would like to call this the spectral envelope of the field, and the phase, the spectral phase being written here as e to the minus I phi omega naught. This has the form of a complex number, where this is the first piece is the amplitude and the rest is the phase of the complex number, in the sense of e to something a e to the I theta, the amplitude times e to the I, the polar angle on the complex plane, if you wish. So, S is then the spectrum of the pulse, not square root of S. So, it is related to an irradiance or intensity in the spectral domain, and phi is the spectral phase. So, phi of t and phi of omega are sort of equal twins, if you wish, which complement each other across two domains. Plotting E tilde of omega and the two E's, E tildes of omega, appropriate to their definition, essentially only means the following: that in one case we plot the spectrum about an artificial zero frequency, in which case we are plotting the deviations from the carrier frequency omega naught on the scale, whereas in the other cases we plot the two pieces omega minus omega naught and minus omega naught on either side, understanding the fact that we essentially these are essentially just with and without the carrier frequency, and that all of these contain the same information. This is just some mathematical jugglery which we resort to based on our need for taking things forward. But the key thing to note is that any of these is a complete description of the pulse, and that the the passport picture of the pulse, if you wish, requires a horizontal frequency axis and two axes which are vertical, the intensity axis on the left and the phase axis on the right, and we ought to plot the intensity envelope, or it could even be the field envelope, but they both are just a square or a square root different from each other, as the case may be, whereas the spectral phase in this case is the other important feature of in doing a complete description of this electromagnetic phenomenon, which is a pulse described through its electric field. Now, often we will use just one of these components, where also the carrier frequency is included, but we can also very well do it without the carrier frequency, and we would still not lose any information, since we just need to keep track of another additional number. So, there is then in the spectral domain the spectrum itself, or sometimes the power spectrum S of omega, spectral phase phi of omega, all of which can be related to the electric field in the spectral domain through these means and equations which we have seen several times by now, which are fairly similar, if not entirely one to one, in terms of analogies with the time domain. Spectral amplitude, there we had temporal amplitude, spectral phase, temporal phase, except that in the case of the time domain we simply drop the adjectives temporal and call it intensity and phase, whereas here we say spectrum or spectral intensity and spectral phase. For a Gaussian, the case is clear, the spectral phase and the temporal phase are both flat, and the amplitude function Fourier transforms from a Gaussian in time to a Gaussian in frequency with the widths related through uncertainty like relations, delta nu, delta t being limited by a constant. And let us remind ourselves that you can adopt the view that the spectral domain is the mother of the time domain, in the sense that a coherent addition of these constituent frequencies, which in this case are 6 discrete frequencies, could be a set of continuous frequencies as well, a continuous set of frequencies as well. And what we see in the time domain as the pulse, considering here simplistic case of the spectral phase identically being 0 across all these frequencies, is that the temporal pulse or the pulse in the time domain is nothing but the manifestation of a constructive interference of these constituent frequencies, giving us, if you wish, an illusion of a pulse in the time domain. But of course, it is more than an illusion, it is really what connects the spectral and temporal domains. And remember, we also understood that if a pulse is propagating and we observe the same pulse which has not undergone any distortion between a designated time t is equal to 0 and a later time t is equal to some t, all that would have happened is that a linear spectral phase, something of the type, let us say some a times a pi or a 2 pi, is added across different frequencies. We considered the example in our earlier lecture, where from omega 1 to omega 6, we simply had omega 1 and 2 differ by 0.2 pi, 2 and 3 differ by an additional 0.2 pi, and kept this difference constant. And we realized just by simple math, visual mathematics even told us, or graphics, a graphical exercise told us that phase shifting is what happens when the pulse propagates from a point here to a point forward in time. While that pulse was nearly idealistic, we have no reason to restrict ourselves to cases where phi of t is either a constant or which we set to 0 in this case. It could be a function of time as freely as one wants it to be, and we can still manage all of that in this formulation. If phi of t is the temporal phase and it contains information of the variation of the frequency versus time, so we can define an instantaneous angular frequency omega instantaneous, or an instantaneous frequency nu instantaneous, as follows: that we take the time derivative of the entire factor which was sitting in the argument to the complex exponential function in the time domain, that is omega naught t minus phi of t. So, take the derivative of that and we obtain there omega naught minus d phi by dt, right. So, while omega naught has a very important position in our frequency domain description, we call it the carrier frequency. Okay. I always think of this as being the one of the main pieces on a chessboard, say the king or the queen, maybe in that case unfortunately the king is omega naught. These are minor but and yet play an important role, d phi by dt, right. So, that plays an important role in the details of whatever follows within the pulse. We can define, or we need to define something like an instantaneous frequency which varies across a pulse in a time window or a spectral window where the amplitude is appreciable, not negligible or not 0, right. So, an instantaneous frequency is of importance when we wish to consider a very general description. It is essentially a very good idea to describe these pulses using the instantaneous frequency in both space and time domains, especially when pulses are short. In as much as we define an instantaneous frequency as d phi by dt, okay, adding or subtracting from the carrier frequency, we can do something similar in the frequency domain to define a group delay, a quantity called the group delay, which is analogous in terms of the fact that it is d phi by d omega. Okay. So, or well, if it is d phi by d nu, you would have an additional factor of 2 pi appearing somewhere. That group delay is the companion of instantaneous frequency in the frequency domain versus the time domain. However, these are not related through an inverse 1 over each other relation. But then, although we have used liberally the concept of a spectral or a temporal phase function phi of t, the fact remains that until you measure this, you do not know this. So, while the formulation rests on its existence and our ability to measure this directly or indirectly, therefore, we must keep this or have this in the sense of a Taylor series which expands this out in terms of successive terms of diminishing strength in terms of a converging series, where the zeroth order term is phi naught, and this is phi 1 is the instantaneous frequency. It is the derivative of, or rather it is not the instantaneous frequency, it is related to it by the fact that it is omega naught. The total instantaneous frequency is omega naught plus phi 1. In certain definitions, it could also be made into the instantaneous frequency, but that is for another day. Let me not confuse you with that. But then the higher order terms, essentially in this case, phi 2 relates to the time variation of a quantity like phi 1. Okay, it is d dt of d phi by dt. d phi by dt at a given time t is equal to 0 is phi 1. The d dt of d phi by dt at the same time t 0 is phi 2. So, it is a measure of how much variation there is in time of something of the instantaneous frequency itself. That brings us to the okay. Oh, okay, very good point. That is a very good point. So, Pratik's question is that in the frequency domain, our description of whatever was happening had like two pieces of a function like that, where this is omega naught, this is 0, this is minus omega naught, right. So, Pratik's question is, if this is the total information in the spectrum, right, correct me if I am wrong, it seems that it is either an even or an odd function. Let me go back up a few slides to get a more accurate picture. Okay, yeah. So, indeed these are like mirrored reflections, right. So, my figure there was inaccurate. So, what Pratik wants to know is, if this is the 0 of this scale for whatever reason, are the positive, and since I have the positive and negative frequency side, where these seem to mirror each other on either side, right. Does this mean that for the complete S of omega, is it plus or a minus S of minus omega? Well, we had essentially S of omega minus omega naught to be one piece and S of minus omega naught, right? Um, so this is omega naught, this is minus omega naught. And so from the looks of it, it looks like this is the total S function from all the way from minus infinity to infinity seems to be even the way we have defined it, right? S of omega, the way we have defined it. Okay. So, yeah, okay. So, the point being, let me copy this expression out over here too, because E tilde of omega is 1/2 S of omega minus omega naught exponent I phi omega minus omega naught plus half S of minus omega naught So, well, it is true that these two pieces, okay, what is this? So, this is a half S1 of omega exponent I phi omega minus omega naught plus half S2, or I should call this maybe S plus S minus where we should write omega goes from 0 to infinity, right? Pardon? Oh yeah, okay. These amplitudes are all under the root sign, which I should define more carefully here. So my total function, but this is the point I was coming to. I have to call this like an omega prime. I'll tell you why. Okay, where omega prime would then go actually from minus infinity through 0 to plus, because omegas are in this representation, omegas are allowed to take only positive values. As such, we only would have bothered about, sorry, we only would have bothered about one piece of this, because This is what we measure, and the rest we do not measure, right? It's a math consequence of the math. But now, if I consider this function as omega prime with this newly defined frequency variable, it is going to be an even function in omega prime. Yes, it looks like an even function, or
I feel like if my original time domain function is purely real, then the Fourier transform might be, then the spectrum might be.
it is always real in the time domain. The electric field is real, right? But then the negative part of the spectrum contains no new information, physically speaking, but mathematically speaking, yeah, if I now use a new frequency like variable omega prime, which can also take negative values, frequencies physically cannot take negative values, then yes, in a complete mathematical description of this type, it is even. However, the point I wish to make is that we run into this idea runs into a problem, in my opinion, if we now talk about E tilde of omega, okay, that is without considering everything in the spectrum, neglecting the carrier frequency omega naught. This piece E tilde of omega, this representation also has the same information, spectral amplitude and spectral phase. Here these functions, we cannot restrict them in being even or odd about the 0 frequency. That these should be symmetric about this is not, I mean, it's physically very restrictive, if I may say so. We have no right to impose that a priori, and no need rather. Spectra can get skewed. A perfectly Gaussian pulse, which is in reality, you can always, I mean, you have to measure a Gaussian and deviations from it and establish how close to Gaussian it is. In reality, those pulses can also be produced, say a transform limited pulse from a very high quality mode lock laser would be very close to a Gaussian or secant hyperbolic, both of which would share this property. However, it is very easy to go from that sort of a pulse to make the spectrum very asymmetric about the frequency where the spectral amplitude is maximum. That is very possible. You go from a pulse which is like that in the frequency domain to a pulse with a spectrum which is like that also in the frequency domain. I mean, you have some conversion, something doing all this stuff, okay. That this can happen is fairly, I mean, fairly easy. You put it through a nonlinear medium, nonlinear optical medium, you typically would generate some frequencies and do stuff like that, okay. S of omega prime, the way we have defined it here. No, it's purely as, okay, that's again the question, like you inverse Fourier transform this, then well, you have negative frequencies, we should check this out more carefully, but by no means are we going to say that you know, this is that E of t is going to have a symmetric envelope about t is equal to 0. Again, that's very restrictive, and we are not going to have that in real pulses. For example, a pulse which is having an instantaneous frequency which is not constant across time is not even in terms of the carrier frequency oscillation. Even the amplitude envelope need not be even as in symmetric about its maximum point. Most real world pulses wouldn't even I mean, would not subscribe to that. But dispersion, for example, dispersion natural to any medium will ensure that even if you start with such a symmetric pulse, the mere act of propagation will lead to the fact that different constituent frequencies will run with different velocities, and hence pulses will quickly suffer a distortion, okay. The broader your spectrum, the more impactful this distortion is, and your pulse will deviate quickly away from 0 into something else. This is something we will see very soon in our discussions. So, yes, good question. However, the point remains that we ought to have a more general description than imposing any symmetry arguments if you wish at this point. Okay, let us jump into